Yihui, you are now in EPFL. The floor is yours.
Right, thanks, Zoltan. So my name is Yihui, and the title of my talk, well, I wanted to call my talk Decoding is All You Need, and I also wanted to call our paper that, but luckily cooler heads prevailed. So the title of our paper, which I'm going to talk about today, is Hamiltonian Decoded Quantum Interferometry. And this is joint work with my wonderful co-authors, Sasha Schmidhuber, Jonathan Liu, Stephen Jordan, Noah Shetty, and Alexander Paremba, who are at MIT and Google. So so the reason why I wanted to call my paper Decoding is All You Need is because of this paper in AI, which is Attention is All You Need. And this was an instrumental insight in AI. I think it was something that is the reason why we are all using ChatGPT today. And for real fans of this work, you can also purchase a T-shirt with this, with this paper on it. And if I am successful in my program, there will be T-shirts with the title Decoding is All You Need. So yes, so what do I mean by decoding is all you need? So this is really a reference to this paper last year called Optimization by Decoded Quantum Interferometry. And the punchline of this paper is that if you want to solve a classical optimization problem, actually all you need to do is to solve a classical decoding problem. And it's a reduction. So what I'm going to talk about today is a generalization of this paper. So I'm going to actually recap what goes on in this paper and then tell you how we generalized it. So DQI is a quantum algorithm for classical optimization problems, and the canonical classical optimization problem that it can solve is max XOR set. And this problem is a problem that gives you a set of linear equations, which are the rows of a matrix, or the coefficients of which are the rows of a matrix B. And let's say that there are m linear equations in n variables, so that B is a m times n matrix. And it gives you like the solutions to these linear equations. However, okay, so what does this actually look like? So B is kind of a tall matrix, and you are given as input B as well as V, but these linear equations might not be consistent, so there might not actually be an x that satisfies all of them at once. So all you need to do is to find an x that satisfies as many of them as possible. So because these linear equations might not be consistent, so it suffices to optimize this objective function f of x, which is simply the number of satisfied equations minus the number of unsatisfied equations. And you want to, of course, make this you want to find the x that achieves the largest value of f. So I'm going to put this at the top right-hand corner of my slides. And so the observation here is that there is one simple way you can think of doing this quantumly, which is to prepare a function state f. Now, again, f is the objective function that you want to maximize. And what is the meaning of a function state f? It is a quantum state that is supported on basis vectors such that the amplitude of the x basis vector is f of x. And so we expect that when you prepare this function state f, the basis vector that maximizes the objective has the largest amplitude on it. And so if you just measure in the computational basis, then you obtain x with basically probability proportional to the square of its objective function. So if the objective function has a high value, then you obtain x with a high probability. And of course, so how does one actually prepare this function state f? Well, so the idea of DQI is that instead of preparing f, you prepare the Hadamard transform of f, because this Hadamard transform is sparse. So the DQI paper says that what you do is you instead prepare the Hadamard transform and then you transform back. And they claim that it's easy to prepare the Hadamard transform because it's sparse. Okay, so you can also think of actually improving this protocol, because what you achieve with this is all you do is you prepare this function state f. But what if there are two bit strings that have approximately equal values? Then you might, with some probability, get the slightly suboptimal bit string, because the f of x1 is quite close to f of x2. So the objective function f might not be very sharply peaked around the optimal bit string. So instead of preparing the function state f, we can also prepare f to the L. So yes, you can also prepare this kind of state in DQI, and this enhances the peak. So the method for doing so is just like the same. You prepare the Hadamard transform of that, and then you transform back. And so I just want to explain one more thing, which is what exactly is this Hadamard transform I've been talking about? Well, so recall that the original problem we want to solve is parameterized by this tall matrix B, which contains all the linear equations, as well as V, which contains all the solutions to the linear equations. And the Fourier transform of this function state is really a state that is a function of this B and V. So if you want to prepare this target state, you can do so in a simple two-step procedure. The first is to prepare just a superposition over all the e's, where the superposition goes up to e's of Hamming weight L. This is a Dicke state, and it's easy to prepare. And then you act with B on a second register to put the value bt times e in the second register. And this is almost the state that we want to get, except that we have two registers, but we only want one register. So we have to uncompute the first register. And the way you do this is that based on the value in the second register, you infer the value in the first register. And by doing so, you can then set it back to 0. And since the first register is now 0 in superposition, so you can just remove it. OK, so the key insight of DQI is really the reason why this is called decoded quantum interferometry, which is that this problem of solving BTE to E is a decoding problem. So as long as you can solve this decoding problem, you can uncompute the first register and then remove it. OK, so this was a real mouthful, so let me just go through it all again. So first, you start off with an optimization problem. The canonical optimization problem is max XOR set. And in this optimization problem, all you need to do is you need to maximize some objective function, f. How do you maximize this objective function? Oh yeah, OK, so the thing I want to say is that decoding is all you need, because DQI is a reduction from this classical optimization problem to decoding. OK, so you prepare a function state f, where this function state has the value of the optimization function for every, as the amplitude for every corresponding bit string. And in order to enhance the amplitude on the optimal bit string, you prepare actually f to the L, and then you measure the state. So DQI says that you prepare the Fourier transform of this state, and then you transform back. And to prepare the Fourier transform of this state, it actually suffices to solve a decoding problem. OK, so there's an important caveat here, which is that this decoding problem is not always efficient to solve. And in general, the only examples we know for which this decoding problem is efficient to solve is for very structured codes, like algebraic codes, like Reed-Solomon codes. So since this DQI is simply a reduction from an optimization problem to a corresponding decoding problem, so DQI is only going to give you an efficient algorithm if the decoding problem is efficient to solve. So a question you might have is, DQI reduces classical optimization problems to classical decoding problems. So why would you need a quantum computer to do this? And the answer is actually that the place you use the quantum computer is that you actually have to run the decoder in superposition, and you can't do that without a quantum computer. So then this leads to an even better question you might have, which is, does the same approach work for quantum optimization problems? And this is where I finally begin to talk about my own work. So what is a quantum optimization problem? It's an optimization problem, but for a Hamiltonian. And I'm going to get to why we call this an optimization problem in a second. So the setting that we will consider is that you have a Hamiltonian, and it's a Hamiltonian which is a linear combination of Paulis with plus or minus 1 coefficients. And what you want to do is you want to find the ground state or the ground state energy of this Hamiltonian. So the reason this is called a quantum optimization problem is that this set of problems completely encompasses all the classical optimization problems we just talked about. And the reason is as follows. For every classical optimization problem of this form, you can write down a corresponding Hamiltonian such that if you find the ground state of this Hamiltonian, then that is going to give you the solution to the classical optimization problem as well. And this Hamiltonian is just a Z Hamiltonian, so it's diagonal. So it's a strict subset of the whole set of Hamiltonians that we consider, where you can have arbitrary Pauli terms. So yes, if you solve this if you find the ground state of this classical optimization problem, it also solves the corresponding quantum optimization problem for this diagonal Hamiltonian. Okay, so DQI showed that for this subset of classical optimization problems, these problems reduce to classical decoding. And what we show is that for quantum optimization problems, those also reduce to classical decoding for commuting Hamiltonians. And for non-commuting Hamiltonians, we reduce them to classical decoding plus state preparation. Okay, so again, let me state the setting of the quantum optimization problems that we look at. The coefficients of the Pauli terms have to be plus or minus 1. And I said just now that the goal was to find the ground state or the ground state energy. But we actually do something more general. We can apply any polynomial function you want to the eigenstates of this Hamiltonian. And so, and we can do this if you can decode L errors on some code that is defined by H. So before I go into the actual algorithm, I want to explain why this is non-trivial. So the eigenvalues and the eigenvectors of H are not explicitly known, and yet we are able to produce a superposition over the eigenvectors of H, where the amplitudes are any polynomial you want applied to the eigenvalues. But we never ever have to actually find out what the eigenvalues and the eigenvectors are in the process of doing this. And to do so would be very inefficient because diagonalizing m by m matrix takes m cubed time, but here m is 2 to the n. So you might also ask, well, this looks very similar to quantum singular value transform. For those of you who know it, could we actually do this via quantum singular value transform if you had a block encoding of H? You could, but then you have to incur this cost, which comes about from the fact that if you want to block encode something, you need the operator norm of that something to be controlled. So then you need to block encode that thing divided by the operator norm. And this just gives you an additional cost where you have to do some amplitude amplification. And we don't have this cost in our method of doing this. Okay, so before I go into the algorithm, I want to say a different thing, which is why do I say that preparing this state is more general than just finding the ground state? Because we can not only find the ground state, but we can do many other things. So we can choose the polynomial you want to apply, depending on what application you want. In some cases, you want to find the ground state. So then you apply a polynomial that is kind of like monotonically decreasing in terms of the energies. And then if you do some kind of quantum phase estimation, you can just measure to get the ground state. Because this kind of polynomial puts maximum amplitude on the ground state. You can approximate it by a polynomial. Good point. So in other cases, you might want to do some Gibbs sampling instead. And so then, note that the state that our algorithm prepares is a purification of the state that our algorithm prepares is on 2 registers. And if you look at the reduced density matrix on 1 register, that's a mixed state. And the mixed state has that form there. So then if I just choose P to be a polynomial approximation of the Gibbs function, we have just done Gibbs sampling. Alternatively, you might want to prepare, you might want to apply any other kind of polynomial to to this state, and then you can do any kind of spectral filter you want. So you can prepare microcanonical ensembles if you want. And so this is a pretty general thing to do. Okay, so our algorithm strictly generalizes DQI in the sense that the state prepared by DQI is actually also a state of the form that I mentioned just now. If you actually look very carefully at the DQI algorithm, then what it actually does is that it applies an arbitrary polynomial to the objective function, which turns out to just be some polynomial applied to the eigenvalue and using that as the amplitude for the corresponding eigenstate. And what we do is very analogous. Now we have a general Hamiltonian, which doesn't just consist of Z Paulis, they can consist of any Paulis, and we apply the corresponding, a polynomial of the corresponding eigenvalue to the eigenstate. So this is kind of like a pretty cool visualization of the actual algorithm, which I will describe right now. So so now I'm going to explain this picture. So the intuition for this is as follows. So let's assume for the time being that the Hamiltonian that we care about consists of Paulis that commute with each other. This is generally an easier case. And so what we try to do with HDQI is we try to prepare the state that is simply a polynomial of H applied to a superposition over all eigenvalues. Now, this is ridiculous because the polynomial of H might not be a unitary, so how do you do that? But there's actually an even bigger problem here, which is how do you even get this state which is a superposition over all the eigenvectors without actually finding out what the eigenvectors are? Well, there is a trick that we use, which is the maximally entangled state, which has this very useful property that the maximally entangled state is maximally entangled in any eigenbasis, including the eigenbasis of the Hamiltonian. And this is true even if you don't know what the eigenbasis of the Hamiltonian is. So what we are actually going to do is we start off with the maximally entangled state, and then we apply a polynomial function of the Hamiltonian to one register of the maximally entangled state. Okay, and then you might point out that a polynomial function of the Hamiltonian is not a unitary, but this is a problem that was already kind of dealt with the DQI pipeline. So essentially what you need to do is that you need to decompose a polynomial of the Hamiltonian into a linear combination of Paulis that you can apply. And then you prepare a different state called the pilot state, which I will not write down, that encodes all the operations that you need to apply, and then you tensor this pilot state onto your maximally entangled state. The pilot state is going to be the control register, and controlled on this register, I will apply operations to the maximally entangled state. So then after that, the third step is where the decoding actually happens. You have to uncompute the register that contained the pilot state, and then you have to remove it, and this is the step where decoding occurs. So HDQI for commuting Hamiltonians is literally just these three steps, and steps 1 and 2 are always efficient. Step 3 could be inefficient because there's an important caveat here, which is that this whole thing is efficient only if the decoding is efficient. Okay, so I've talked so much about the decoding problem, but what exactly is the decoding problem that you need to solve? Well, the decoding problem is a decoding problem that you write down depending on what Hamiltonian you have, and here is how you write down the decoding problem. So it is defined by this parity check matrix, so it's a fat matrix, and every row of this parity check matrix is a symplectic representation of one of the Paulis in your Hamiltonian. So if you have m Paulis in your Hamiltonian, we need m to be greater than n because we want this to be a parity check matrix, so it has to be fat. And in general, our algorithm works when m is polynomial in n. So this is a 2n by m binary matrix, where every column is the symplectic representation of one of the Paulis in your Hamiltonian. And the decoding problem is simply, if I regard this as the parity check matrix, I want to decode, basically that means that you, given this matrix times like some message y, if you are promised that the y is of weight L, where L is the degree of the polynomial that you want to apply, you have to recover what y is. And this is just like the syndrome decoding problem. Okay, so just to recap, I'm going back to this picture. So what we do is we start off with a maximally entangled state, which is the torchlight there. And then you can think of HDQI as some kind of algorithm that applies different weights to the different eigenvectors in the spectrum of a given Hamiltonian. And what's actually powering this algorithm is that it's secretly running a little decoder inside it. Okay, so we also have an extension of this algorithm to non-commuting Hamiltonians, and it's unfortunately a lot more complicated. And the reason it's complicated is because the Hamiltonian is now non-commuting. So when you write the first step, where you decompose P of H into a linear combination of Paulis, this step is significantly more complicated because x times z is not equal to z times x. And you cannot arbitrarily swap around the order of the terms. And so yeah, the set of operations you need to apply has like some complicated coefficient that depends on like the anti-commutation structure of the Hamiltonian. So then, what differs between the HDQI for non-commuting and for commuting Hamiltonians is that now the second step is also very complicated. preparing this pilot state is not efficient in general and could take a very long time. So now you have two bottlenecks, preparing the pilot state and doing the decoding. So the statement here is that for non-commuting Hamiltonians, HDQI is efficient if and only if both of these two steps are efficient. Okay, so I've talked a lot about how this pilot state is quite complicated for non-commuting Hamiltonians. Is it ever the case that this pilot state preparation is efficient? And the answer is yes. So this depends on the anti-commutation graph of the Hamiltonian. So what is the anti-commutation graph? Given a Hamiltonian consisting of a bunch of Pauli terms, I'm going to create a graph where the vertices are all the Pauli terms, and I put an edge between two vertices if the Pauli terms anti-commute. And so, as an example for this Hamiltonian with Z1, X1, and Z1, Z2, I put an edge between Z1 and X1 because they anti-commute. And I put an edge between X1 and Z1, Z2 because they anti-commute. And I do not put an edge between Z1 and Z1, Z2 because they commute. Okay, so the pilot state is actually an MPS. And the anti-commutation graph determines the dimensionality of each of the qubits in the MPS. And the point of this is really that if the anti-commutation graph is simple enough, then these qubits are very small. And so the preparation time for this MPS is going to be polynomial in n times this q here. And q is 2 to the size of the maximal connector component of the anti-commutation graph. And the bond dimension is L plus 1, where L is the polynomial that we want to apply. So this was quite surprising to me. But of course, this still doesn't tell you for what Hamiltonians this is actually efficient to prepare. So you might ask the question, what's the use of all these reductions? Are there actual Hamiltonians for which your algorithm is efficient? And fortunately, the answer is yes. Because what we show is that if we have a spin glass defected with some quantum terms, which means basically we have like a Z Hamiltonian where you choose terms with probability P to put some X terms inside. Now the X doesn't commute with the Z, right? So we call these defects. If P is small enough, then the largest connected component size in the anti-commutation graph is small enough. And so the MPS is simple enough to prepare. And we also give some classical algorithms for Gibbs sampling some stabilizer code Hamiltonians. And the story is actually that we wanted to find an application for our commuting HDQI. We found a simple structure. We found that some stabilizer Hamiltonians have a simple structure that allows you to use commuting HDQI to prepare the Gibbs states or ground states. But then we dequantized ourselves because we discovered that this same structure also allows you to classically Gibbs sample from these stabilizer code Hamiltonians. So to our knowledge, this is the first time that anyone has come up with classical algorithms for Gibbs sampling from these stabilizer code Hamiltonians. Okay, so that's basically all I wanted to say, and we have lots of open questions, so happy to work with any of you on this. And obviously, I think for those of you from a complexity theory background, the Hamiltonians that we have only plus or minus 1 coefficient, so you're pretty familiar with these Hamiltonians, but apparently that's not the case for Hamiltonians that people actually care about in practice. So it's an important question whether any of this works for physics and chemistry Hamiltonians. Can we extend HDQI to fermionic Hamiltonians? This is something we have tried to do. So far, we have not succeeded. And what are the complexity theoretic implications of HDQI? So yeah, with this, I open the floor to questions.
Thanks a lot for this inspiring talk. There are already some questions. Could you
Can you comment on, I hear many rumors and some papers were on the archive recently that question whether DQI with a classical decoder cannot be dequantized in broad generality. So can you comment on this a bit? So what kind of guarantees or reasons do we have to believe that as long as we use a classical decoder in superposition, that DQI cannot be fully dequantized?
Okay, so now I'll comment on DQI, but not HDQI.
Yeah, sorry for the question.
Yeah, but that's a great question.
I guess it's related, right? Because if DQI fails, then maybe...
Well,
HDQI is also in danger, or not necessarily?
HDQI is a generalization of DQI, right? So,
Okay, so if okay, then maybe I rephrase my question. If DQI fails with a classical decoder, HDQI can still bring a quantum advantage.
So yes, there are actually multiple facets to this question. So the first is that, to my knowledge, the dequantizations of classical DQI are on average over optimization problems. But that is also not where we expect the advantage in DQI to be. I think because we don't really have efficient decoders for an average code, so I wasn't really expecting DQI to give me an advantage for a random code. Instead, all the examples of DQI giving you advantages are for very structured codes. And in the DQI paper, they have this optimal polynomial intersection problem on which they showed that DQI actually it beats all classical algorithms they found. And the reason that this problem was a problem on which they found quantum advantage was because this problem is just a problem of decoding a Reed-Solomon code. So it's a very structured problem, and I think what we've seen is that you can only really expect DQI to give you advantages on structured problems. So now I'm going to talk about HDQI. So there is actually something that HDQI does that these attacks on the regular DQI doesn't do, which is that HDQI prepares the Gibbs state. Now, these attacks on classical DQI, or like the original DQI, are for preparing the ground state. So it remains open if these attacks can also be extended to HDQI. So to summarize my answer, my very long answer, the first point is that these attacks are only for random problems, whereas I think that the advantage should only be found on structured problems. And the second is that these attacks are for ground state problems, whereas HDQI can also do Gibbs state problems.
Thanks. Any? Okay.
Is there any intuition or some sort of enlightening example where the decoding problem shows up naturally, or you sort of have some understanding of the decoding problem that shows up in these Hamiltonians?
Well, I think that because I didn't really explain how the decoding problem works, so it's like also a little bit difficult for me to like give a natural example. But basically, the decoding problem is defined by like putting the symplectic representation of the Paulis in as the columns of some matrix and treating that as the parity check matrix. So for certain kinds of Hamiltonians corresponding to quantum codes, if you do this, then that parity check matrix actually has like pretty high rank. So like in that case, then the decoding problem can be solved with belief propagation, basically.
So I also have a question that you ask here, can we extend HDQI to fermionic Hamiltonians? So, I mean, if you just simply take a very good fermion to qubit mapping, let's say the ternary tree mapping, where you have, let's say, only logarithmically many or weight logarithm Pauli strings encoding normal fermionic Hamiltonians, and then for certain cases you can then analyze because you have the same anti-commutation graph. For quantum chemistry, it's going to be very dense, so not good. For let's say some lattice models, it's going to be good. Isn't that a reply to that, or you want to make an HDQI even more inherently fermionic when you ask this question?
Oh, I think that's very interesting. I think I just didn't know of these lattice models for which the anti-commutation graph is not dense.
I mean, Fermi-Hubbard model, right? It's not super dense, that anti-commutation graph.
Oh, okay, yeah, maybe that works. But yeah, I think it would also be nice to just like do it natively for fermions.
Yeah, that's true. Okay, so
I think Marcin has a question.
Yes.
Yeah, I also have a question about the anti-commutation graph.
Mm-hmm.
This parameter Q, what is the typical value like for a random, let's say, random selection of M Hamiltonian, which has M randomly chosen Paulis? What's the typical
Oh, I would
value
expect this parameter Q to be like quite large. I mean, like if you just randomly choose Pauli strings, they're probably going to anti-commute, and they're not going to commute.
Yeah.
Yeah. But I mean, I don't think this is the last word on the issue. I think like there's probably a way to significantly simplify our algorithm for non-commuting Hamiltonians. But there are also some barriers to doing so, basically. There are some complexity theoretic barriers. I don't think you can do it for a general non-commuting Hamiltonian, only for very structured ones.
Thanks. So any final question? If that's not the case, then let's thank you again and all the speakers. And